Okay, so good morning, everyone. So I think this is where we left off yesterday, where we discussed the notion of a universal horizon, which is a leaf of the preferred foliation, which blocks everything, including perturbations that propagate at arbitrarily high speeds, because they have a modified dispersion relation. And I showed you yesterday how that was found by solving the equations of the low energy limit of Ozawa gravity in their full glory, but also you could also look at the behavior of the foliation. So you could also look at the equation for the T field that I showed yesterday in Schwarzschild, and you see the same effect. Now, one important thing that I didn't say yesterday is that, of course, I showed you the relation. I started from Einstein ether theory, and I said that if you impose that the ether is hypersurface orthogonal, then before the variation, which means you're going to a different theory, there is no real equivalence, right? Then you get the low energy limit of Ozawa gravity. But of course, that means that even though the theories are not the same, it turns out that hypersurface orthogonal solutions will be shared. So a solution that is so in spherical symmetry, basically the ether is automatically hypersurface orthogonal, and hence the solutions of the Ozawa gravity are also solutions of Einstein ether theory. Okay, so that solution that I showed you, the behavior of the solution that I showed you, holds for both theories. Things become different when you start including rotation. So when you rotate your black holes, and I mean that has been shown for slowly rotating black holes, but obviously by continuity it will hold for more fastly rotating black holes. Einstein ether theory solutions don't have a preferred foliation. The ether doesn't want to be hypersurface orthogonal. And whereas slowly rotating black holes in Ozawa gravity, of course, always have a preferred foliation, and they also turn out to have universal horizons. So that's not a property, some sort of weird property of spherical solutions. It's a more generic feature. In fact, people have looked also in three-dimensional black holes, where it's easier, I mean, to look at arbitrarily rotating black holes and find explicit solutions and so on and so forth. And universal horizons persist there. I mean, this is supposed to say even with not flat asymptotics, right? And also, it has been shown that you can have universal horizons that lie outside de Sitter horizons in cosmology. So there seems to be sort of a complete analogy between horizons in relativity and these universal horizons. So when we did the GR part in the first half of the week, I went on to give you the global definition of an event horizon in general relativity, right? So, you know, you can think the same way here and say, okay, I mean, in spherical symmetry, I could operationally define a horizon by looking at the foliation in a similar fashion that I did that by looking at Edington-Finkelstein coordinates and light cones and so on and so forth in GR. But what about solutions that don't have any symmetry? I mean, is there some other definition of the universal horizon? So in particular, is there a global definition of the universal horizon? Then also in the GR part, I talked about killing horizons and how event horizons, at least for stationary black holes of general relativity, are killing horizons, which provides, it's not a local definition of the horizon itself, because the converse is not true, but at least, you know, it characterizes the horizon locally. It gives you some properties of the horizon. Is there something similar here? Could I say something locally about these horizons, right? And also, these horizons are sitting, where are these universal horizons? When I'm supposed to find these universal horizons? So I mean, in these spherical solutions and the rotating solutions we've looked at, as I said, there was a succession kind of killing. If you looked at the low energy limit the propagation of every mode, where the dispersion relation became linear, then they were propagating in these effective metrics. So you could go and find kind of the killing horizons of these effective metrics, and the universal horizon was always sitting further in, right? Is this always the case, or could it be at some point outside, and hence these are some relevance for astrophysics, I mean, or whatever, right? So I think all of these are interesting questions, which we later try to explore. So to go towards the definition, the global definition of the universal horizon, you have to, of course, rethink of all of the definitions that we gave. So we'll have to do kind of a tour de force of what we did for GR, start again from, so how do we define causality? How do we define past and future? How do we define horizons, basically black holes and so on and so forth? And so the logic here is to consider a manifold, which instead of just being, so in GR, your space-time is your manifold and the metric. Here you will have the manifold, the metric, and the preferred foliation. So you have a foliated manifold, which is the picture that you have in Hosovo gravity. And then a bit of definition here. We want this foliation to be ordered in a sense that, so every event should lie on some leaf of the foliation, and every pair of events will have a unique causal relation. They'll either lie on the same leaf, so there'll be simultaneous events, right? Or they will be in another leaf, either later or earlier, right? I'm not labeling the foliation. I'm not saying that there is preferred labeling. So because I want to be able to reparameterize, right, the time. So I'm just saying that it's ordered. So, and hence there is a time, a notion of time basically defined with that foliation. So then you can define causal and acausal curves, right, as we did in GR by using light cones. But now in terms of this foliation, so you can think of a curve, if T mu is the tangent to the curve, and U mu now is the normal to the foliation, then you can take the dot product of the two, and you can say, oh, look, I mean, if there's zero, then obviously the curve lies on the leaf, so it is acausal, it's connecting simultaneous events. If it's positive, then it's future directed. If it's negative, then it's past directed. So it's pointing over the leaf or under the leaf, right? So, and that defines causal curves in the foliation. And then you can think of the future and past. So in the left, there is the picture I drew on the blackboard before for general relativity. You know, you look at an event and you think of its future, and its future lies, of course, in the future cone. This is the effect, the events that it can affect, the events you can reach by what we call the causal curve at GR, time, like, or null geodesics, right? Okay, yeah, so here's the picture of general relativity, right? So this is J plus of P. And of course, if you, instead of one event, you were considering a set of events on a space-like surface, that would be the future of P in general relativity. But now the picture is quite simpler. If you have an event P that lies on a leaf of the foliation, then everything that is north of the leaf is in the future, right? And everything in south would be in the past. And again, if you have a set of events on the leaf, then again, they would have effectively the same future, everything that is on the north. So this future and past is simple in this case. Right, then we need to discuss about asymptotics, right? So in general relativity, we're assuming that the metric is asymptotically flat. Now we have a foliated manifold, so you can define basically this projector, which is the induced metric on the leaves, right? And what you can do is you can conformally extend the manifold like we did to create the Penrose diagram and compactify to bring infinity to a point, right? And I'm talking about the three space now, every leaf, right? And then you can use the usual, I didn't talk about this here, but the kind of the usual GR definition of asymptotic flatness, where we mark infinity to a point, and then you discuss about the behavior around that point, and you define asymptotic flatness in this way. So this is developed by Geros and others, I mean, in GR. So you're asking basically for the leaves to be asymptotically Euclidean space, right? And then by this compactification, you can, of course, for every leaf, you can talk about the point at infinity, because you've mapped all of infinity to one point, which is kind of the equivalent of I naught in this case. And then you can take all of this, and then you did some condition about the foliation as well. You need to talk about how the foliation behaves, right? And that comes in the guise of what we call the trivially foliated asymptotically flat end. So the logic is that when I go far away in every leaf, so if I take all the leaves and stack them together in a sense to make the space-time again, the foliation should be the trivial foliation of Minkowski, where basically your foliation becomes the time coordinate in Minkowski and it doesn't do something funny, right? Because you don't want the foliation to have structure in flat space. Okay, so then you can define this M in brackets as the open region in which this holds true. Every leaf has a trivially foliated asymptotically flat end, right? And then you can take all of these points at infinity and join them together in a line, which is where your leaves end when you've compactified, right? And now this is now a line, right, which is your infinity. And I will call that scry in the same way I was calling scry future null infinity in general relativity. But of course, it's a different thing, but it is actually the relevant notion here. And if I do that, then interestingly, all of the definitions that I had in general relativity hold. If I think of, I can define the horizon, right, the future event horizon, or the future universal horizon, in the sense as I call it here, as the boundary of the past of my scry, and I can define past universal horizon as the boundary of the future of this scry, right? And the intersection of the two would be all of this M in brackets, right? Which would be effectively the exterior. I mean, and then it follows, you can prove that, and you can also, based on these definitions, and then you can also prove that both of the universal horizons, right, would be leaves of the foliation themselves. You don't have to assume that, it follows, and also that they're boundaries of this region. And then you can define the black hole in exactly the same way as you did in general relativity, and the white hole in exactly the same way, right? And a kind of a key takeaway message is that these universal horizons are leaves of the foliation that fail to reach infinity, this scry, right? So basically the picture that you have is you've taken the space-time and you've basically foliated it with leaves. This defines your causality, right? All of these leaves reach infinity. So they span basically the whole space-time up to infinity, but then suddenly a leaf appears that doesn't actually reach infinity, and this plays the role of the universal horizon because it closes up and kind of demarcates a part of your space that is not causally connected to infinity. Okay, so again, as I said yesterday, I think I find it quite remarkable that you can actually, if you just use the appropriate definition from the beginning, you end up with the same definitions for all of the quantities in this direct analogy, even though here you don't have relativity really, you don't have special relativity. Okay, then you can think about, okay, as I said, in stationary spacetimes in general relativity, event horizons are killing horizons. So let's see what happens here in stationary spacetimes. So let's define stationarity, right? And I mean, of course, you have to adapt the definition a bit, but I mean, I'll call here stationary spacetime a spacetime that has a killing vector that is causal in some open set chi that overlaps with that hat version of that bracketed version of my manifold, right? So there is a stationary region, which is the same. So in GR, we'll say a killing vector that is time-like near infinity, right? So this would be the analogous statement here. There is a stationary region, And I'm saying that it aligns with the ether. If the ether, I mean the normal to the surface here, asymptotically. That is the trivial foliation asymptotically, right? The trivially foliated flat end, right? And then if you do that, then you can prove that the normal to the foliation u dotted with that killing vector chi is 0. So if that holds true, and this is the acceleration of the vector, if this, so this is completely defined by this is u grad u, right? Dotted with chi is not 0, then that forms a set of necessary and sufficient conditions for a hypersurface to be a universal horizon. So in fact, this locally characterizes the horizon, right? And it turns out then that that chi becomes m, and this killing vector is unique. And of course, there's complete analogy here with killing horizons again, because that would be so in GR you would have chi dotted with itself is 0 is the killing horizon, right? And interestingly, this sorry, and you can also prove that this quantity will be constant along the universal horizon. So I didn't talk about surface gravity here. I kind of mentioned it a little bit, but basically on a killing horizon there is a quantity called surface gravity, which is constant across the horizon. Is being used in black hole thermodynamics and other things, right? So in analogy, in GR you would have here chi dot with itself is equal to 0, and then you would have that quantity that is constant surface gravity. So this plays the role of surface gravity, and in fact people have gone later on and shown that, which is constant. This kind of replaces this condition and in fact becomes effectively a local definition in this case of the universal horizon. And the case where this wouldn't be 0, sorry, the case where this would be 0 would kind of correspond to what it would be a degenerate horizon with 0 surface gravity. Okay. Yeah.
With respect to a preferred foliation, right?
No, the killing vector is a killing vector. It satisfies Killing's equation with respect to the metric, so in the usual way. And then if I have this killing vector in that region, then I call the space-time stationary. If the killing vector is just causal, that is the only relation to the foliation. Instead of imposing it to be time-like, I'm just saying that it's causal with respect to the foliation. This is the relation with the foliation.
I'm wondering, say, if you take the integral curve of the killing, say rotation related to that, you already said the foliation might not be invariant under t equals to t tilde, right?
No, I said it is invariant under t equals to t tilde.
Okay. So
yeah.
Then the integral curve would also. Yeah.
I said it is. I'm not imposing anything about this. Okay. So again, that pushes the analogy even further to this. A quick point about the last thing I said. So where does the universal horizon lie? Does it have to lie inside killing horizons of this, nested light cones of the linear version of the dispersion relation? So if you assume axisymmetry as well, so phi would be now your killing vector with closed orbits, right? Then it will end up satisfying these conditions with u and a. Then you can prove that the universal horizon will lie inside the killing horizon always. And you can prove that by using these two killing vectors to construct a linear combination of them in this way, and then showing that this killing vector will be null, a normal to a null hypersurface somewhere outside the universal horizon, and that involves Carter's rigidity theorem. You basically, which is used in GR basically to do something similar. Okay, so I'm not going to sketch the proof, but you can show that the universal horizon, colloquially speaking, will lie always inside a killing horizon, or you're not going to find a rogue universal horizon. So, which makes sense because you're talking about modes that propagate with modified dispersion relations, and the logic is the lower momenta that are propagating slowly are blocked by a killing horizon before, and only the higher momenta can cross that, and but again, eventually they will hit the universal horizon. Okay. Okay, so some perspectives. So obviously the new notion here is and I think unexpected notion before it was first encountered, is the notion of a universal horizon, and the fact that you can have black holes without relativity, without special relativity. It's the causal structure is highly non-trivial. I mean, there is a lot of discussion about, okay, but how does that thing form from collapse? Can I take these theories, collapse something, and form the universal horizon, right? And there are, in fact, there is a numerical simulation of spherical collapse in Einstein ether theory, which was done before people understood that universal horizons exist mathematically, right? But it was done, so you could think, oh, I'll go back there and see if there was traces of the universal horizon, but in fact, it was done in, so if you're in the foliation that I'm talking about, right, the universal horizon is infinitely into your future. So it was done in this foliation, so you're kind of approaching it, but it's not clear if you're reaching it. So the way to probe it would be to actually try to do the simulation in a different foliation so that you can see the formation, right? This hasn't been done yet for technical reasons. There is the question, okay, is this structure stable? And this question arises from the fact that if you think of setting an initial value problem on this foliated spacetimes, and you have this universal horizon, then it's not hard to realize that this is actually, you know, a Cauchy horizon for that problem, in a sense that you can't evolve data past that horizon if you stick to that foliation. And the reason is kind of simple. As I showed, you can prove that it's a leaf of the foliation that doesn't reach infinity. But I told you earlier also that there is an instantaneous mode, there is an elliptic equation in that system. So if you formulate as an initial value problem, you get a set of, even in the low energy limit where you don't consider the lower or the higher order dispersions, you have basically second order equations where there is a set of hyperbolic equations like in general relativity, a set of elliptic equations that are constraints like in general relativity. These constraints are preserved by time evolution, so you can solve them in the initial slice. And I mean, if you're doing free evolution and forget them afterwards, right? But there is also this elliptic mode, this elliptic equation that you need to solve in every slice to propagate your data. And this needs boundary conditions. And if you have an asymptotically flat manifold, it needs conditions at infinity, right? But if the horizon is a leaf that doesn't reach infinity, then you can not provide conditions there. If you're prescribing data at infinity, when you hit that, there's not going to be a way to continue the problem unless you try and prescribe data wherever that leaf ends, basically, right? So in this sense, you can think of it as a Cauchy horizon. And Cauchy horizons in general relativity are believed to be unstable, right? So could it be that this is unstable as well? And in fact, something else happens there, right? So that's a very interesting question. Because I said it's a Cauchy horizon, I mean, should you be thinking that there is no space-time, no foliated space-time beyond it? I mean, that's the end. It's the, you know, it's the end of all time, basically, for in these kind of theories. You can ask yourself if, then you can go to a lot of philosophical questions. Do we need the universal horizon? I mean, if it's a Cauchy horizon or whatever else. I mean, because we can't really, it's infinitely in our future and so on and so forth. There are two there's kind of an interesting consideration in Lorentz violating theories of black holes. People have tried to create, because, so forget about the universal horizon, put it to one side for a moment. Think of these nested structures of horizons, then people have tried to violate thermodynamics by using this in the following sense. If you think of this nested structure of horizons are killing horizons of different effective metrics for different excitations, then in fact, once you cross the first one and you go inside, right, this behaves like an ergo region for the asymptotic observer. But I mean, this is an ergo region where the field that is blocked by the first horizon basically, sees it at the horizon, but a faster propagating field can still come out. So you could think of, oh, actually, I can send in I can send in a particle, then it splits into two particles, one made out of the slower matter that falls in, and one made out of the faster that comes out again, right? And that is kind of a version of the Penrose process run between these two horizons, right? And hence, could I actually mine energy of what actually could be a spherical black hole here? So I'm not really mining angular momentum. So people had argued that this way you could build a perpetual motion machine, so that if something is fishy here, and then they tried to construct also kind of, in fact, that one came first, trying to use Hawking radiation from the two horizons to construct this. And what I describe is kind of the classical analog of it. I mean, I think, although this is very interesting, there are kind of serious caveats. So, I mean, it's been shown that in the Penrose process, the trajectories actually don't exist if you look carefully. The geodesics to do this don't actually exist, that reach infinity and so on and so forth. But there is also kind of a conceptual issue here. Think of the Penrose process, you're mining angular momentum, right? The assumption in violating thermodynamics, the second law of thermodynamics, is that this actually doesn't kind of mines mass and hence reduces the entropy rather than increasing it, but actually there is a non-trivial configuration of the field that defines the foliation, your scalar or your ether outside, right? And in fact, you're changing that as well. So it's not entirely clear unless you look at the back reaction that you're violating anything. It's based on a very simplified assumption of thermodynamics. So I mean, this is kind of, again, something interesting to think about. And I mean, this kind of philosophical question, does it all matter, refers to first of all, constraints on Lorentz symmetry, right? So is Lorentz symmetry really violated? Can I really afford it to be violated? And I'll talk a little bit more about that later. And then that second paper here is has been looking at binary. So it started trying to look for, to model binary black holes in this theory to kind of produce waveforms, right? But I mean, in order to do that, they were trying to understand how a slowly translating black hole behaves, because that's part of the calculation. And then they realized that when they were trying to kind of calculate a solution for a slowly translating black hole, they were getting singularities appearing on the horizons, and in particular the universal horizon. So that created some doubt. Actually, is it that when can this be a problem? Can it be that when I start moving my black holes in the foliation, then these structures are not stable or whatever? That is not clear. It's not clear if, say, the slowly translating approximation breaks down because the foliation is kind of global and you need to think of the problem differently, or it is actually a problem and people are looking into this as well. Okay. Okay. So I'm done with Lorentz violations. I'm now going to switch gear, and for the remainder of this talk, I want to talk a little bit about how all of these things that I talked about as examples, I mean, could get imprinted in observations, and particularly into waveforms like this one that gravitational wave detectors pick up. Okay. So I'm not going to talk about. I deliberately, I will avoid to talk about constraints on any specific theory or model and so on and so forth, because that's not what I'm interested in. I'm interested in kind of giving you a flavor of qualitatively of how does new physics of this type get imprinted in gravitational waves. So how do you, obviously we do a lot of things trying to test GR with gravitational waves, and the most obvious thing you would do is, of course, null and consistency tests. Does GR fit the data? Is GR consistent with the data? Can I take two separate parts of the waveform, say the in-spiral and the ring down, and do parameter estimation? Do they match? So is everything okay? And that that is good because I can do it using only GR waveform models, right? Then you can do kind of unmodeled searches. I'm not having a specific theory in mind, but I'm trying to just look for stuff in the data that might be there. Obviously, these have a lot lower sensitivity and accuracy in picking up deviations. Or you can do parameterized tests, which I've underlined because this is kind of the main way in which people are extracting specific constraints on specific theories at the moment, which means I try to parameterize deviations from a GR waveform in some way, and then I'm trying to constrain the parameters of this parameterization and extract bounds, right? So this works particularly well in propagation of gravitational waves. I'm starting from, I have a source here, it's propagating to the detector. While it's propagating, if the space-time it's propagating in is not the expected one, and it's different, then of course the waveform will change on the way to the detector, and hence I can parameterize that because that's just changing the dispersion of the wave, basically. So, and I'll talk about this later. So that works particularly well there. It works also fairly well in the in-spiral, the parameterized tests, because of course, again, the in-spiral is fairly simple. It can be treated perturbatively, so it's easy to create like these post-Einsteinian parameterizations to pick it up, to pick up deviations. So, all of this are being done because obviously there's a huge advantage. You don't need to know how you're deviating from GR. You can just be agnostic, and they're very efficient in this way, right? Of course, parameterizations have disadvantages as well. They only get you halfway to where you want to be, because if I create some generic parameterization and I constrain a parameter, I don't really know what I've constrained. So I'd have to map it back to a theory and figure out, what that constraint really means, right? It can also give you a false sense of achievement, and because constraints can be meaningless or not independent. And by that I mean I start and I say, let me parameterize. Like think of I don't know, the post-Newtonian expansion in static spacetimes, right? Of course, you can have a lot of post-Newtonian parameters, but if I take a theory and it has one coupling that deviates from GR, all of these parameters depend on that coupling, right? In different ways, obviously, but they depend on that coupling. So if I look at my parameterization, I can say, okay, I did that experiment and I tested and I extracted a bound on the first of that parameters. And then I did another experiment in a different regime. So that first experiment didn't give me any constraint on the second parameter, but it gave me a very strong constraint on the first one, right? Then I do an experiment in a different regime that now manages to constrain the second parameter as well to some, but it gives me a loose constraint. I'm hailing that as a victory because, oh, look, it's the first time we constrained that parameter. Now, when I translate to my theory, in fact, because of the dependence of the two parameters on my coupling, the very strong constraint on the first parameter, which is lower order in my parameterization, in fact, continues to be a much more stringent constraint on that coupling constant than what I got. So I didn't really get anything by doing that. right? And I mean, an example of this is what I told you before about Brans-Dicke theory and why people were interested in binary pulsars, because of course you say, oh, look, we're looking at more strongly gravitating systems, but I mean, the two neutron stars are strongly gravitating, but they are separated by a good distance, so the interaction between them is really weak, right? And if I go and, in Brans-Dicke theory in specific, and avoid solar system tests by tuning the parameter to be high enough, then I'm not going to get anything from pulsars, even though I think, even though I think I'm testing a new regime. If I were to do some post-Keplerian stuff, I would get constraints in parameters that I wouldn't have gotten in the solar system, but they wouldn't mean anything in the context of that specific theory, right? So this is what I mean by a sort of false sense of achievement. So I want you to remember now that plot that I showed in my first slide with the various experiments. And this is what I meant, that I mean, there is a third dimension here, that all of these experiments have a certain sensitivity. If you think them of as independent, oh, I'm testing gravity in this curvature, I'm testing gravity in that curvature, then okay, you can be happy that you're putting some constraints in such type of parameterizations. But again, if you think, oh, there is some underlying theory, I mean, there has to be some underlying theory. It might not be my favorite one, but there is some underlying theory that that should fit all of these experiments, right? And it has a certain number of theoretical parameters. Then the sensitivity with which you measure the parameters in each of these experiments is very important, because you can extrapolate, right? And it's very important, and it might be that an experiment at lower curvatures, lower potentials with very high sensitivity gives you better constraints than going to that corner. So that's the big caveat, right? Which is the same basically that I'm saying here, right? And the final disadvantage potential here is that, of course, parameterizations have a range. So PN expansion of the metric static spacetimes, of course, is a weak field limit, doesn't hold if I'm going to do strongly gravitating objects. PPN formalism for modeling the in-spiral will break down in the late in-spiral, and so on and so forth. So QNMs will break if you go sufficiently back in the ring down, and so on and so forth. So this is important again because you can't extrapolate and connect different regimes and get combined constraints in the same parameters, which of course give you a bit stronger constraints. I mean, what more could you do? Well, you could do, of course, theory-specific tests as well. You can take a theory and say, okay, can I actually produce waveforms or pieces of waveforms for that, and try to compare with the data directly and constrain the parameters directly. Of course, there is an obvious disadvantage of this, that you have to do it for different theories, right? But the advantage there is that this way you could actually interpret your results in the context of the theory, right? But also it could give you some general lessons. For instance, like if I have an example of a theory that does something, like the scalarization I gave you, then you say, oh, actually, that's interesting. We could look for it in the data. If I've never found an example of a theory, I might have never have thought that this might happen, right? Also, you could calibrate or inform your parameterizations, which is, again, scalarization is a good example of that. As I said, I mean, people are trying to generalize things like EOB models which are effective descriptions of the waveform, to include things like scalarization and sudden jumps in the behavior and so on and so forth. And of course, if you do a theory-specific test and you get a full waveform, you could actually probe parts that are very hard to parameterize, like the merger part of the waveform, right? The ring down, where people are trying to parameterize, there might be ways to parameterize, but it's much harder than the inspire. Okay. And it is important to probe these parts as well, because different parts of the waveform probe different physics. So let's think about that now. So I mean, I'm assuming you're all familiar with the fact, of course, that this is the in-spiral, this nonlinear part is the merger, and this here is the ring down. And of course, we split them because we model them in different ways. Okay, so let's go step by step through what would you have to do if you had your favorite theory that is deviating from GR on the standard model, but now you have a set of field equations with some certain number of fields. You say, okay, what do I do to constrain this theory with gravitational waves? So, I mean, the first thing you would need to do is you need to study compact objects at the stationary limit and understand their properties, right? And you do this for two reasons. First is because, I mean, if they don't deviate from GR much in the stationary limit, then you're probably not going to find much deviation in the waveform. So that might not be the most interesting theory to start with, which is what I discussed extensively in the last few days. That you can try to find the interesting cases, right? But you also want to do it for a different reason. So the signatures you're looking for is, you know, hair of some type, I mean, non-trivial field configurations. Maybe the tidal properties of compact stars could change and so on and so forth. Now, the second reason you want to do this is if you think of the in spiral or the ring down, which are the parts that you can treat perturbatively, you need to perturb around something, right? And so you need to understand how stationary configurations behave because it's the basis of your perturbation theory for the ring down, but also for even for the in spiral. I mean, if you're doing, think of the simplest case where you're doing it post-Newtonianly. At the end of the day, you treat them as point sources, but of course the parameters of your expansion will depend on the structure of the stationary objects, right? So any back mapping will require understanding how this works. Then to model the in spiral, you can, I mean, this can be done, as I said, in a post-Newtonian way. Of course, there are much more sophisticated ways like UOB to do this, right? And what you're looking for, but I mean, this is kind of well understood, and you can just extend the standard techniques. And what you're looking for is new polarizations, because you have new fields, so you have new channels of radiation, right? Dephasing of your signals. So you take two compact objects, suppose they have an additional field dressing them up with respect to GR, so they have some sort of hair, right? Think of the scalar case that we discussed as the typical example. So I have two black holes that are dressed with a scalar configuration, they're orbiting each other, the scalar fields interact as well, so they emit scalar waves, right? As they emit scalar waves, the system loses energy faster than it would in GR because now there's an additional channel of radiation. That affects the orbital dynamics, which means the evolution of the orbital frequency is different than in general relativity. And of course, that evolution determines the gravitational wave frequency of the traditional polarizations, right? This is what this dephasing refers to. So in fact, even though in most theories we're considering the scalar radiation doesn't actually interact with the detector. It interacts extremely weakly with the detector, so you wouldn't detect it directly, that polarization. You can actually detect its effect by the cumulative effect it has on the conventional polarizations, because it changes the orbital dynamics and hence it modulates the signal, right? And that piles up over the in spiral. So if you look at the whole in spiral, you can get very strong constraints from this. And I'll come back to that actually later on. Then later in the in spiral, you can start probing tidal effects and so on and so forth. Then you would want to model the ring down, which you can do with, as I said, perturbation theory around that non-trivial background that you should have understood before. And what you're looking for is, of course, QNM spectrum, the quasi-normal mode spectrum, and you're going to talk about more quasi-normal modes in the tutorial this afternoon. So quasi-normal modes, of course, unlike normal, I mean, they're like normal modes in a perturbed system. They call them quasi-normal because, of course, there's dissipation. And what you expect here is that you will have a shift in the frequencies, and that will signal deviations. So here is the first big complication. So if you try to do, so as you will see this afternoon, if you try to take a black hole in general relativity, Kerr black hole or a Schwarzschild black hole, and you try to perturb it, and you look at the equations that determine the perturbations, even in Kerr, which is far more complicated than Schwarzschild, you can find the right basis in which the equations become separable. So you can split the time and the spatial parts, and you can expand in spheroidal harmonics and so on and so forth. And the perturbations decouple, the modes decouple, and hence you can do the analysis fairly easily, right? But that is a property of the D'Alembertian, the box operator in Kerr spacetime. And which goes back to the symmetries of the Kerr spacetime, which has, in fact, a hidden symmetry. So apart from just being stationary and axisymmetric, there is an additional symmetry that leads to additional conserved quantity, which is called the Carter constant, right? Because it was discovered by Carter. And it relates to objects, an object called a Killing-Yano tensor, basically, rather than just a Killing vector, right? So it is this property that this symmetry, extra symmetry of Kerr, basically, that allows you to do this. If you deviate from the Kerr spacetime, so in a hairy black hole, right, or black hole that is not a solution of general relativity, there is no reason that this property will be maintained. So there is no reason that you will still have separability in your equations, which makes the treatment a lot harder. And you might not be able to do calculations in a frequency domain. You might actually have to do a time evolution, kind of like just evolve initial data directly in the linearized equations and so on and so forth. So in certain kind of approximations, slow rotation and so on and so forth, you might get back separability, and people are obviously looking into that. So it's much harder to do that bit than it is in GR, right? And it's not, you know, in many theories, we don't still know how to do this efficiently. And of course, the hardest part is always the merger, because their perturbative techniques don't work. So we need to do full-blown numerics, right? Because of this, and because we haven't done that in most theories, we don't really know what to expect. It might be that not much happens, basically, right? In GR, the merger is sufficient, for two black holes at least, seems to be kind of disturbingly simple. You do all of these numerics, and at the end of the day, you're not getting something too exciting. And here, the big complication is, of course, the initial value formulation. How do you set up an initial value problem in your favorite theory? And is it well posed? And I'll come and discuss that towards the end of the talk in some detail, because I think that's a very interesting problem in this context. Okay, so these are your steps. So I said before that you get different physics in different parts of the waveform. So now that I've explained the parts of the waveform, it's easier to explain that too. So if in the Erlang spiral, what do you probe? Well, you would probe very easily massless fields, because if you make them massive, they get confined. So if you have two objects, they're separated widely. If you have a massive field, then its configuration won't extend all the way to the other objects. You aren't going to have any interaction of this field, and you're not going to have any radiation in that polarization, right? So you won't be able to detect anything, right? So in the very early spirals, you can only probe massless or extremely light fields. And of course, you'd have to have an appreciable charge for the interaction to be important, basically, right? As of course the object gets closer, you go in the latent spiral, you could potentially probe smaller charges. So even if you have kind of lesser configuration, basically, you could still potentially see it, right? And you could probe more confined fields. I mean, still they have to be very light, because we're talking about kilometer-sized objects at best. But you could probe slightly larger masses. And of course, in the latent spiral, you start probing the object's structure. So that is already true in GR for neutron stars. So you're hoping to use the latent spiral to probe the tidal deformabilities of neutron stars and try to say something about the equation of state. And it's equally true for anything else. You could tidally disrupt, say, any cloud you have around. So if you have a black hole dressed with a cloud, you cannot tidally disrupt the black hole itself, but you could tidally disrupt the cloud, and you could see that in the data. So maybe you could probably even more confined fields in this sense. So in the merger, I mean, the key word is nonlinearity. So if somehow there's not some nonlinear effect that enhances these fields, these new extra fields, then maybe you're going to see something happening there, right? Or if the merger causes some burst of radiation in the new fields and so on and so forth, then you could see that there. And in the ring down, obviously you're probing the final object, which interestingly doesn't have to be the same as the original object. So think of the case, think of scalarization again. I talked about spin-induced scalarization, right? So you could have a theory where only highly spinning black holes would be scalarized. So think of a merger of two black holes, which are, the original black holes are not spinning very fast, so they're not scalarized. They have spin, say, 0.5, right? They merge. In the merger, you're going to get about 0.7, 0.75 spin anyway, because you're converting orbital spin to the spin of the final black hole. So the endpoint black hole will be scalarized. So if you're looking only at the inspiral, you're not going to see anything. But if you look at the ring down, then you should actually see that this is not a Kerr black hole, right? And you could concoct scenarios that is the reverse. You're starting, say, so think of not spin-induced scalarization, but the most conventional one. You start with two black holes. Their masses are large enough. They're small enough to be just left of that threshold of scalarization. So they're a GR black hole. But when they merge, they form a larger black hole. So it's pushed above the threshold, and hence the final black hole it needs to descalarize. So we are starting. Sorry, I said it wrong. I think they're left of the threshold, so they're small enough. They're scalarized. Then they merge. They form a larger black hole. It's right of the threshold. So now GR is the stable solution. So it has to lose its hair. So there you would expect that there is some shedding of hair in scalar radiation during the merger and ring down, and then you're left with actually what is a Kerr black hole. Okay. Now, what I said focused primarily in kind of comparable mass binaries and fairly small mass ratios, which is what we actually kind of see now with LIGO, right? And as I said, I mean, in the current state of affairs, the stronger constraints in any theory that we had come actually from the inspiral. And so you have the two comparable mass objects. They orbit around each other. If they're charged in any other field, then they emit radiation in this new polarization. So if they have, say, a scalar monopole, which is the case we discussed here, they emit dipolar emission by the interaction in scalar waves, right? And as I said before, that will be additional energy flux, changes in the orbital dynamics, and a modified waveform for the traditional polarizations, and that would give you the strongest constraints. The deviation piles up as you run into the spiral. So the longer the spiral, the better it is, and you get strong constraints from that, right? So this is seen currently as kind of the best way to constrain such scenarios, right? But I mean, you don't only have comparable mass binaries. You could have binaries which have very high degrees of asymmetry, and if you push that to the extreme, you go to what we call extreme mass ratio in spirals, where you have a very small object orbiting around a very large black hole. So these will be typical sources of LISA. You have a few solar mass object, a black hole or a neutron star. It's orbiting around a supermassive black hole, like the one in the center of our galaxy, 10 to the 5, 10 to the 6 solar masses, right? And then the mass ratio is extremely small, defined as this. You can also find it defined the other way. So you would say extremely large, right? So the conventional thinking over a period of years for this is that the kind of what you were looking for with these systems is that you have a very long inspiral, obviously because the particle is orbiting around the black hole many, many times before falling in, right? And it stays in the LISA band for like more than a year. So you have like orders of magnitude longer and in spiral than what you get now. And I mean, at leading order, if you ignore radiation entirely, then of course this would be a geodesic orbit. But because of gravitational radiation, it deviates and it kind of very slowly creeps into the black hole, right? And the idea was it maps very precisely the space-time because it performs so many orbits. It gives you a map of the space-time of what we call so we call this the secondary and this the primary. So it gives you a map of the space-time around the primary, and you can perform tests by checking if this space-time is actually here, right? So that is the conventional thinking. Now, combine this though with what we learned earlier about massless scalar fields and how the charge scales with the mass, right? So, okay, we said that the theories, first of all, you could have no-Her theorems in which the black hole will be Kerr, so there's nothing to detect in that case. So you're going to learn nothing by only looking at the space-time of the primary, right? But also, at least for a massless scalar field, the only exception would be to have the charge introduced by that coupling with a Gauss-Bonnet invariant, but then the charge is fixed and the charge scales with a mass, right? If you have only the Gauss-Bonnet invariant, then if you add any other extra shift-symmetric terms, it's still determined by this relation. I mean, I'm saying this quickly because we went through it carefully before. And at the end of the day, you end up with a situation that even if you take the most general case and you do some scaling analysis, you realize that the charge per unit mass still scales like 1 over the mass squared over that coupling constant, right? I'm writing here everything in geometric units, so basically everything is a length. This has dimensions of a length squared, so if you divide here by m, you get the charge per unit mass being some dimensionless parameter, right? And basically it scales like 1 over the mass square of the black hole, right? And the characteristic time scale, length scale you're comparing with it is your coupling constant, right? So if you push to the large m limit, then you're going to get a completely negligible charge. But the interesting part here is, of course, this is already constrained by other observations. I mean, and we know that it can be larger than kilometers. So solar masses basically size, right? So for supermassive black holes, that's entirely negligible, as 10 to the minus 5, basically, from already existing constraints, right? So in fact, just by doing theory, you know that at least for massless scalars, you can have any appreciable charge in a very large black hole, right? So there's really nothing to test with that example for MRIs. So if you were to think about this, you'd say, okay, MRIs are just hopeless, and I'm going to get much better bounds by comparable mass binaries, right? And in fact, for testing at least these massless scalars, LISA would be completely hopeless because also comparable mass, larger black holes would be more weakly charged than smaller ones, which are the ones LIGO is already detecting. So there's no reason to try to probe scalar charge with LISA. This would be the naive take, right? But there is a catch with that. And the catch is the way people are thinking about these MRIs. So yeah, at the leading order, the small guy is probing the space-time, right? But in fact, if you think one order higher in perturbation theory, then if that guy carries a scalar charge, then this guy is, apart from being a mass orbiting the other mass, is also a charge which is accelerated by the gravitational field of the central object. And accelerated charges radiate, right? I mean, if I take an electron and start swiveling it around, I'm producing electromagnetic waves. So there is scalar emission actually in this system produced by this. And in fact, the emission is always the difference. Dipolar emission, even in a system like that, is the difference of the two charges. So the fact that this is 0 means just that this guy is producing all of the radiation, right? And same as in the case of the comparable mass, right? This guy will emit scalar waves, which means the system is losing energy faster than in GR, and hence its orbit will be affected, and hence the conventional polarizations will be affected. with the big advantage, the fact that you'll observe this guy for a year rather than, you know, fractions of a minute. So that should be a big effect, in fact, right? It's higher order, but it's a big effect. And indeed, it turns out that if you follow this through, the fact that you can argue that in this case the central object is effectively Kerr to a very good approximation, you can do a consistent treatment in the mass ratio. So I'm not going to go. I don't have time, so I'm not going to go through this in general. But as I said here, you can think of this. You can express everything here in terms of the mass ratio and the charges of the two objects, and then you can do a consistent treatment perturbatively as you do in general relativity in the mass ratio, and show that that what I intuitively said is in fact precisely correct. You can model the radiation as that of an accelerated charge. You can then calculate the effect that this has in the orbital dynamics of the particle, and then calculate the deviations in the waveform of the conventional polarizations, the spin 2 polarizations, and compare this with what you expect from LISA and extract constraints which are stronger than what you already have from comparable mass binaries of the same mass. So in fact, MRIs are a very good way to probe charges, right? And I mean, this is a little bit of a paradigm shift, because the way people are thinking about MRIs is that they're used to probe, as I said, the central object, but actually this is probing the small object. So you can do tests of, you know, for looking for new fundamental physics, thinking of the properties of the smaller object than the larger one. Okay. Okay, so I'm going to skip some technical details and go back to propagation. So I said before that one of the kind of the parametric tests we do are propagation tests. And this is really what we're testing in this case. This is the dispersion relation of gravitational waves. I'm not going to call them gravitons because they're classical, but this is the dispersion relation of gravitational waves, right? So if you had GR, this here doesn't exist, the higher order momenta. Here I mean, I've kind of slightly switched notation, and I'm not using omega mk, I'm using energy and momentum, right, P. So this would not be there in GR, and of course there is no mass, right? And this, sorry, yeah, this C, of course, would be 1, right, in general relativity. So now you go and add by hand all of the other corrections, you parameterize it, and then you can say, okay, can I actually go and check what's happening in reality, and can I impose bounds on all of these coefficients, right? So basically, characteristic energy scales where these deviations appear, the mass of the graviton, and here the speed of propagation of gravitational waves. And of course, you know, the strongest constraint of this comes from, so you can in general, you can constrain the speed of gravitational waves on its own. You can constrain the other things. So you get a strong bound on the mass of the graviton on M1 and on M3, these energy scales, right? Constraints from here onwards start becoming quite weak because the energy of the waves is very, very low, right? I mean, these gravitational waves. So you can probe these scales with high accuracy with a very small energy wave, because of course you're trying to probe higher powers of the dispersion relation. You'd need a high energy excitation to probe this with some accuracy, right? But even though you get strong bound, even the strong bounds you supposedly get, I mean, strong has to be quantified. What does strong means? You know, yeah, you're saying that these are very small in some arbitrary sense, but how interesting are they? Well, the mass of the graviton, the constraint, is not really ruling out massive gravity theories for what we wanted them to be. I mean, massive gravity theories, we're constructing them to have a very small bound of very small mass in the graviton, because we wanted people wanted, you know, that mass to be relevant cosmologically, obviously, to solve cosmological problems and so on and so forth. So even though the bound is kind of very strong in absolute terms, several orders of magnitude, I mean, you know, it's not the strongest bound we can get from any sort of experiment, and it's not really ruling out massive gravity models, right? The bounds on M1 and M3 are, again, are strong, but I don't know any kind of very interesting theories that have these terms, because this requires both violations of Lorentz symmetry and parity invariance, right? Because they're odd order in the momenta. Now, the stronger, of course, constraint that comes out of this approach is on the speed of gravitational waves from the binary neutron star merger, because it had an electromagnetic counterpart, right? So you get a constraint by thinking of the speed of propagation of gravitational waves versus so arrival of electromagnetic waves and gravitational waves and the difference between them, which, of course, because you have a very, the constraint becomes stronger and stronger with the distance, the propagation time, right? And because we have the source is very, very far, you get an extremely strong constraint here, which is written here, right? And that has been used to rule out certain dark energy models that required non-trivial cosmology. So they required basically, I mean, they were based on Discordansky theories. You had the non-trivial gradient of a scalar field in cosmology, which was driving accelerated expansion. But this also meant that you have a different speed of gravitational waves because they were effectively propagating in some effective metric that was a composite of g mu nu plus the gradients of the scalar field, right? So this is again, remember that this is basically the change in the speed. To have an effect here, you need a different propagation. So either you need a modified dispersion relation in general, because fundamentally you've changed the dispersion relation in gravity, or it's because the wave is interacting with something between source and detector in the same way that if I take light and it passes through a medium rather than in vacuum, of course, it propagates at a different speed, right? And so if there is a field in a non-trivial configuration, because you want it to lead to a non-trivial cosmology, and the gravitational wave interacts with it on the way here, it can change the speed. And this is what was happening in these cases, right? So if you think in terms of a model like of a Lorentz breaking theory, where you could have technically many of these terms, like Einstein-Ether theory of Horava gravity. So this definitely poses a very strong constraint in one direction in their parameter space. So remember, Einstein-Ether theory, for instance, had 4 coupling constants, C1, C2, C3, C4. A combination of some of them determines the speed of gravitational waves. So this means that that combination needs to be very heavily tuned to satisfy this constraint, right? But of course, it's a very large parameter space. So it basically, in the worst case scenario, you can fix the speed to be exactly 0 and reduce the parameter space to 3 dimensions, basically from 4, right? Similarly, Horava gravity in the low energy limit has 3 parameters. So this effectively reduces it to a 2 parameter space plus a width of 10 to the minus 15 for the third, right? Of course, that requires tuning then to be in that bit. I mean, again, I said I don't want to discuss about constraints in any specific theory, but very, very briefly, these are the 2 in Horava gravity. If I were to fix the speed of gravitons to be exactly 0, right, then this would be basically the other dimensions in the parameter. So I'm fixing it exactly 0. So I'm now left in a 2-dimensional parameter space. This will be the speed of gravity in the other dimensions, right? And then you can think of other constraints, weak field, I mean, stability, or whatever else you want, right? And you end up saying that I need to be in the gray area, and so then I have to say something about that scale of the higher order operators that controls L4 and L5. So that's basically values of the wedges. That also induces a constraint. I don't want to talk in detail about the constraints, but the point I want to make is you need to be inside the wedge and in the gray area, basically, right, to be viable. And these lines corresponds to the speed of the scalar mode, which is, I don't remember in which direction they're going now, but one is 10 times the speed of light, 100 and 1,000 times the speed of light. So you can see that even though you're restricting the parameter space very much and you have to be in some corner, right? The scalar excitation still can propagate, even at the low energy limit, 1,000 times the speed of light, basically. So that makes you wonder, okay, have I really constrained Lorentz symmetry breaking? Because I mean, I can still propagate extremely fast. I mean, even though I'm in that specific corner of the parameter space, right? There is, of course, a question here of tuning. Can I tune in the low energy limit my theory to be in that corner and still be viable without having to worry about quantum corrections and all that? Okay, so in the remaining time, I want to very quickly talk about nonlinear evolution. So I mean, I said what I had to say. As I said, I wanted to speak very broadly and generally about observational tests, but to do all of these things, I tried to argue before how it is important to actually try to get some waveform in some specific theories as well, even if just to understand how different it can be from general relativity, basically, and if it can have drastic departure in some small part of it, and so on and so forth, right? So how do we actually do that, right? How do we solve the equations in their full glory, including the nonlinear regime? And that brings up the problem of well-posedness. So I mean, if I have if I have a set of PDEs and I want to set up an initial value problem, then I want this initial value problem to be well-posed, which means I want the solution to exist, to be unique, and to be continuously dependent on the initial data. I don't want to make a kind of tiny change in the initial data and then the solution becomes something widely different than before. This needs to be quantified, right? I mean, and it gets quantified by Sobolev norms and all that stuff. And I mean, be well posed in one norm and not well posed in the other. But of course, these are all subtleties. We don't need to discuss them today. So, I mean, this is a very sensible requirement that has to do with predictivity. I want my classical theories to be predictive. So I should be able to say, this is what's happening now. I should be able to predict then what is going to happen in the future. Okay. It took a very long time to prove that GR is well posed. It was only started, first results appeared by Sarkar in the 50s, and then of course, they were worked by others as well. And then it took another 50 years from that point until we could actually do the first black hole merger numerically. So that's not an easy thing to do. The problem when you deviate from GR is that even though you can find kind of deviations like standard scalar tensor theory that I showed you before, that kind of are readily well posed with the tools of general relativity, mostly because they can be reformulated as through field redefinitions as GR plus matter. So think of the passage from the Jordan frame to the Einstein frame. I end up getting Einstein's equations with the scalar field non-minimally coupled to matter. So it's clear that everything can be done in the same way as in general relativity. Finally, so all of the interesting cases are not obviously well posed. And I want you to now go back and think of what we discussed. So let's think first of the principled approach. So Lorentz symmetry, right? You have faster than light propagation. So there's very big deviation from GR, right? You're not even sure if your equations are hyperbolic, right? I mean, so you don't have standard wave operators basically for your perturbations. Massive gravity, right? You need to have at least two metrics to have consistent models. So again, this doesn't seem vanilla at all, right? If you want to violate parity in gravity, then you get dynamical Chern-Simons gravity. It has third order field equations in derivatives, right? So again, this is not the vanilla type, right? Screening mechanisms, I mean, I didn't talk here about Weinstein screening, but I mean, there are screening mechanisms that require a lot of nonlinearity in derivatives. So your derivative structure is very different. And in fact, the Noether theorems that I showed told you that I can only get interesting black holes beyond GR. I can only get black hole hair if I have couplings between the scalar and curvature. And in fact, the Gauss-Bonnet invariant, which is quadratic in curvature. So even though that leads to second order equations, these equations are have more derivatives in general. They're quadratic in the second derivatives, in fact, right? So this departs from a fundamental property of Einstein's equations. So Einstein's equations are quasi-linear as partial differential equations, which means they're linear in the second derivative, right? And this is all of their good properties come from there. You know, generally they are non-linear PDEs, but because of this linearity in the second derivatives, they have very nice properties. And it is these properties that we use in, you know, to set up an initial value problem in the way we do and prove theorems about it and so on and so forth. In general, most of the interesting theories, even if they don't violate any of these, by example, we've learned that they actually lose this quasi-linearity, right? So we can use the technology and the results from general relativity to discuss well-posedness and initial value problems. So that it has taken a lot of work to actually address this problem, and this has started only very recently, right? And the reason this people only started working on this recently, even though, I mean, alternative theories of gravity are around since the 60s, 70s, if not since the 20s, is because, of course, people said, this is a hard problem. As I said, it took so long to solve it in GR. People said, oh, we better find a very good theory first before actually going that far with it, right? And also, there wasn't really so much need to discuss the nonlinear regime before you started wanting to produce waveforms or mergers. So Einstein ether theory has actually been shown to be well posed, right? Even though it's Lorentz breaking. Horava gravity is a very different beast, right? And in general theories with a preferred foliation, as I told you before, there is an elliptic equation that is not constrained. So it's a mixed problem. It's elliptic hyperbolic. So there's part of the equations that should need to be treated as an initial value problem, but there is also a boundary problem attached to it, right? And so in certain setups, it really reduces basically to solving the elliptic problem separately, and then you have a well-posed hyperbolic problem in the guise of Einstein ether theory, but it's not as yet completely clear if that's the general setting, and hence if there are issues with well-posedness. And sometimes things are just complicated. So in this non-quasi-linear scalar tensor theories that are the interesting ones, right? People have shown that in fact they're not strongly hyperbolic in the weak field limit in the harmonic gauge, right? Or some sort of generalized harmonic gauge, right? Which was kind of a discouraging result at first. So if that was happening, if they were quasi-linear, this would be the end. Because with quasi-linearity, you can take the weak field results and trivially translate them to the full-blown problem. But in fact, things are a lot more complicated here. So, I mean, it has later been shown that, in fact, you can find more general cases in which the weak field limit is well posed, right? And so there are numerical results that kind of in the harmonic gauge, obviously, verify this. But now there are numerical results in more generalized cases which have well-defined evolution, right? So this last bit, I mean, I kind of said it in detail to highlight the fact that the initial value problem, the well-posed initial value problem, is not a property of a theory, it's a property of a theory plus an initial value formulation, right? Foliation, gauge choices, and so on and so forth. And you really have to find the right foliation. GR itself is not well posed, obviously, in all gauges. So there are various approaches trying to deal with this problem of well-posedness and trying to extract nonlinear predictions from theories beyond GR and the standard model. And kind of an easy way easy and fast way to do this is to do a perturbative expansion in the couplings. So if you think of the theory that I showed before, say Einstein-Hilbert action plus canonical kinetic term plus that linear coupling to the Gauss-Bonnet, there is a coupling constant there. If I set that to 0, I clearly get GR plus a minimally coupled scalar field. This is a well-posed problem. I can solve it, right? Then, so I can solve that non-linearly. Then I can introduce the coupling and I can treat it perturbatively, and I can calculate a perturbative correction on that coupling constant on that fully non-linear background, right? And I can continue to do that for higher orders, and that is a well-posed problem, and hence I can do non-linear evolution in this way. It's of course an approximation. It captures the non-linearity of the background space-time. It's effectively a linearization on the scalar because the corrections to the scalar come from these extra terms. And also, you can go out of the range of validity of that perturbation theory if you have things that are growing during the evolution. You can have secular growth of things. So it is a way to get some first results, but it's obviously not the optimal way. So here are kind of waveforms that have been produced for scalar waveforms from hairy black holes orbiting each other, basically, that have been produced in this way. People have suggested, and I'm not going to go in any depth in this, but I just want to mention it because it's a very interesting direction, that you could actually fix the equations to render them well posed. So this is something that is coming, the intuition coming from hydrodynamics. Hydrodynamics is, of course, an effective theory. We know that there is an underlying microstructure in the fluid and so on and so forth, and need statistical mechanics and other things to describe it. But if you think of a relativistic fluid and you turn on viscosity and you go and look at the equations that determine the evolution, in fact, they're not well posed. But of course, we all know that that relativistic fluids can be viscous. So this is something that exists in nature. It's just that the equations are in fact a gradient expansion. And because you've truncated that expansion at a certain order in derivatives to describe your physical system, right? You get spurious degrees of freedom. And these are the ones that spoil the well-posedness. So that has been dealt with by trying to kind of remove these spurious degrees of freedom from the equations and render them well-posed by hand without really affecting the physical degrees of freedom. And one of the methods is was introduced by Israel and Stewart. And the logic was that basically you introduce some additional fields and you dump them exponentially in the evolution to kind of take away all of the badness of the problem and leave you with a nice well-posed problem, right? So obviously you need a prescription to do this, and you need to handle it with care so that you don't actually affect the physical aspects of the problem. But there has been efforts to translate this technology to gravitational theories and try to fix the equations in this sort of Israel-Stewart-like approach, right? And it's something that is starting to give interesting results as well. And this relates to the logic of the fact that, again, a classical gravity theory that contains additional fields is really some effective, it's coming out of some appropriate limit of a deviation from GR of the standard model, and it's really an effective theory. So you shouldn't take it too seriously because they're missing terms there. So the well-posedness of the theory, the ill-posedness of the theory is not really a statement about the theory you're looking at, but about your truncation you've done, right? Finally, I mean, and ideally, what you could have is that you can have a proper 3+1 formulation that deviate, that is not, you're not using the standard gauges, you're introducing kind of additional kind of technology to deal with the numerics and so on and so forth, that can actually render your problem well posed, and you can evolve. And in fact, people have done that. So that's what I was saying before, that people have introduced novel 3+1 decompositions that use kind of composite metrics, I mean, with combination of the fields and so on and so forth, and showed that these are well posed, at least for sufficiently small values of the coupling constants, and then evolved successfully data. And here you see waveforms of black hole mergers basically obtained in this way. So there's a lot of progress here. And this is really kind of a new frontier in general in numerical relativity, evolving things beyond general relativity, basically. And I'm going to show you this just one example here because it relates to what we said. So what we're doing here, let me go very quickly back, and I'm almost done. I just want to remind you of the action, which is very far back. Yeah, so I'm looking at this theory here, right? So it's a scalarization theory, and I'm doing spherical collapse. Okay, so I'm collapsing a scalar cloud to form a black hole in the context of this theory. So remember what should happen here. What should happen is I start with certain initial data, flat scalar in Minkowski spacetime. I push it in, basically, and it collapses. And so it should form a black hole. So I mean, if I don't put enough energy, then it will just dissipate and it should leave Minkowski space. It will just move to infinity. But if I push it hard enough, or I put enough mass in the cloud, it will collapse into a black hole. And then that black hole, if the mass is small enough, it's going to be scalarized, because this is a scalarization model. If the mass is larger than that, and I exceed the threshold, it will be a black hole of GR. This is what I'm expecting to get, right? And I have included this coupling to the Ritzi, but I'm going to set it to 0 for some of the simulations, and I'm then going to turn it on for other simulations, right? Okay, so what you see here, this is a value characterizing the initial data. So as you go higher, basically you get more energy in your initial data, right? And these are values of the coupling, of that coupling beta to the Ritzi scalar, right? The other coupling has been scaled out, as I said in the beginning. So I mean, you can, as I've said previously, when we were doing the stationary solutions, you can scale it out with the mass of the initial data and the final black hole, so you kind of get self-similar behavior. Okay, so for beta equals 0, so the green boxes, so this here is a collection of the outcome of the simulation. I start it, I run it, and then I see what the end state is, right? And the green boxes are flat space, right? The black circles are black holes. The red crosses is I lost hyperbolicity during the simulation. I couldn't evolve any further. So the problem wasn't really well posed, right? For this type of initial data. And I mean, some yellow stars up here are some ambiguous cases that we couldn't infer the numerics. We'll just ignore them. Okay, so for beta equals 0, what you see is that you start from small enough energy in your data, and you just go to Minkowski space. They dissipate as they would in GR, right? But then suddenly, as you try up to pile up more energy, you just end up having a region which is in your space-time in which your equations are non-hyperbolic and you can evolve any further. You lose hyperbolicity, right? And this is in line with previous simulations, actually, that try to do collapse without the beta phi square R term. Then if you push the data a bit higher, actually you don't see that anymore and you form black holes. But then again, if you go to larger, what you would expect to be larger black holes, again, you lose hyperbolicity and you can't trace the evolution anymore, right? So your theory is not well behaved. And now I start cranking up the value of beta, so changing the theory a little bit by adding a counter term. And what you see is that, first of all, in that region, I don't lose hyperbolicity now, and I can actually eventually, with large enough beta, trace the evolution, and it's nicely converging to Minkowski space. So the cloud dissipates, basically, as expected, right? And again, up here, I get the same. I start getting black holes, right? So this demonstrates the effect of actually choosing the right counter terms. I'm not trying to convince you that this beta phi square R term is going to solve your hyperbolicity problem in all settings. This is a spherical collapse, so it's a very, very minimal thing. But it tells you, if you don't put the right counter terms, you might end up concluding that this is not a good theory because I'm losing hyperbolicity too easily. But actually, it's just because you didn't have the whole theory, right? This is the takeaway message here. What you see here on the right is a snapshot of the radial profile of the scalar at two different times, right and left, and what you're so that's the red line, right? The dust blue line is the static configuration that you expect to get at the end just by solving the equations with the static limit, right? And what you see now is that the configuration goes in one case. So you see different cases here. This is a case with lower energy in the initial data, where the configuration dissipates to Minkowski space, right? So this is a specific one of the simulations. I think it's this one, right? It's a configuration. You start with smaller initial data and you dissipate to Minkowski space with a flat scalar as expected, right? Then this is here a case with large mass where you form a black hole. This dust line here is the apparent horizon, right? And then what you get here is that the scalar becomes constant at the end. So that's a Schwarzschild black hole that you're actually forming, right? And here is a configuration where the end point has a smaller mass below the threshold, and indeed the configuration goes to the a non-trivial radial profile that matches the static scalarized solution. So indeed, you can trace it and you can indeed see that you form the scalarized black hole when you expected, and the flat and then the Schwarzschild when you don't. Okay. Okay. So so the open issues in that part is that it's a hard thing to establish well-posedness, right? And there's a lot of ongoing work in this. You need to be careful on how you interpret what you ask yourself. Do you want these theories to be well posed for all values of the coupling, all initial data, all physical problems? My take would be that this is a very big ask because these are effective theories. It's not the full theory, right? And indeed, what you can see in all of the numerical simulations is indeed that depending on the initial data you choose, they are well posed. In some cases, they're not well posed. In others, depending on the value of the coupling you choose, they're well posed. In some cases, they're not well posed in others, which in fact is exactly, if you think about what you would expect from an effective field theory. So if you think of an effective field theory in the linear regime, which is what we're used to, then you would say, oh, there is a cutoff in momenta, basically, because I have corrections. They were suppressed by some mass scale. I mean, say the mass of the field I integrated out, right? And hence, I don't trust the theory over this mass scale, right? But here you're doing nonlinear theory. So first of all, there would be the cutoff. And secondly, if you try to do, say, an effective theory for perturbations around one vacuum and around the other vacuum, the cutoff will depend on the background. If your background has scales in it, then this can change what the cutoff is. So here we're doing nonlinear theory. So in a sense, the equivalent of the background is the initial data, right? And which can effectively involve scales in them. How much energy am I putting in the data and all that? And hence and then there are coupling constants in my theory that are dimensionful. So it's the combination of the two that will tell you whether this is a good effective field theory. So in my opinion, I mean, losing well-posedness is really a statement about, oh, I've exceeded the range of validity of this effective field theory as a nonlinear EFT. And of course, there are big numerical challenges associated with doing this anywhere, right? So I'm going to stop here. This was my last slide. Thanks very much for listening. I'll have to take questions.